All right, here we go. It's the last day of class. The only meeting we have left after this is our final exam. So the exam is going to be taking place on Monday, May the 6th from 1 to 3 p.m. It's right here in this room. At that time, just like the last exam, you can bring whatever you want as long as it does not use electricity. You can use it during the exam. So bring whatever you want, bring your notes. You are welcome to use those on the exam. So what I'm going to do today is kind of just do a quick little overview of the topics that we've covered in the second half of the class since the last exam. We'll do a little bit of review of that, and then I'll open up the floor and see if there's any questions or if you what topics you guys would like to discuss for the rest of the time. So let's go ahead and dive in. So the first thing that we talked about way back after the last exam was this concept of transactions. So why do transactions exist? Why do we have them? Yeah.
Because more than one user could be trying to access the data and do something to the database at the same time.
So we have transactions to manage concurrent operations, multiple people using the database at the same time. And so transactions are really just a collection of operations that are going to be performed on the database. We say that transactions have a set of properties called the ACID properties. Who can give me one of those 4 ACID properties? Go ahead.
Consistency.
Consistency. So the C stands for consistency. What does that mean? What does it mean when we say transactions have consistency or help with consistency? Yeah, go ahead. I'm sorry? For no conflicts? Well, actually, we are going to have conflicts. That's a fact. We'll talk about conflicts in just a little bit. What does it mean when we say transactions help us with consistency? Yeah.
It means that in almost any given time, the data in the database are stable and correct.
Okay, so we're moving in the right direction now, right? The way transactions work, it's a collection of operations, right? But either all of those operations are going to run or none of those operations are going to run. And so the consistency comes into play when we say that it's actually, I think, consistent state is the way that it's officially defined. It means that our transactions are going to start in one consistent state where the data all is consistent with each other and matches, and end in another consistent state. But in between, we may not have consistent data, right? While the transaction is operating, the data may not actually be consistent, but it's going to start in a consistent state and end in a consistent state. All right, what's one of the other ones? We got 3 more. Go ahead.
Atomicity.
Atomicity is what the A is. So what is that referring to?
That means that for everything that's in the transaction, it's all or nothing. It's 1 unit.
Yeah, that's the all or nothing properties of transactions. Yep. We got 2 left. Can we get somebody else for one of the remaining 2? I am happy to wait. Yeah. Independence, not quite, but I think that that's close enough to a synonym of what the I typically stands for. It's actually isolation is the I. So what are we talking about when we say that transactions are isolated? Yeah, go ahead. They don't know about each other, so the transaction is going to operate the same whether it's the only transaction or whether there are thousands of other transactions also executing at the same time. It's going to operate the same way. All right, we got 1 letter left. What does the D stand for? Durability. Yep. So what are we using to enforce durability with our transactions? Yeah. Up to date. There's a particular tool that we use though for this piece. Refers to a particular part of the database system. It's actually on the slide right now. I'll wait, you guys. I will stand up here for 80 minutes. Yeah. Log files, thank you. Yes, we use log files to track every single operation that's taking place on the database so that once an operation happens, we know it's going to be permanent. If something crashes, if something gets in the way of the proper operation of the database, we can refer back to the log files and recreate those operations. All right. So then we spent a lot of time talking about how to actually schedule transactions. So we talked about things like conflicts. So what are the two types of conflicts we're going to run into? Two flavors. Yeah, what's up? Read-write conflict is one. What's the other one? Write-write conflict. Yep. And so when we're scheduling, we're actually trying to create a schedule that is conflict serializable. So what does that actually mean when I say that a schedule is conflict serializable? Go ahead, John.
It means that you get the same conflicts that you would get in your current schedule as you would as if every single transaction was serialized.
Right, so it's going to give me a same set of conflicts that a serial schedule would. That's right. And so we have mechanisms for detecting conflicts and checking to see whether a given schedule is conflict serializable or not. But we also talked about in class how we actually don't do that in practice. We don't actually go through the process of creating the graph and mapping the conflicts out. Rather, we use another technique to ensure that the schedules that are being generated are conflict serializable, and that mechanism is locking. So we talked about a few different types of locks. The ones that are used most in practice are read locks and write locks. We talked about those two types of locks. We talked about the typical locking mechanism, the way that those locks are used. I can have as many read locks out for a piece of data as I want, but only one write lock can ever be issued for a piece of data at a given point in time. And then we spent a lot of time talking about various forms of two-phase locking. So two-phase locking is the technique that guarantees that the schedule, if we follow two-phase locking, it will guarantee that we are going to generate a schedule that is conflict serializable. But there are many different ways of doing two-phase locking. I think some of the ways that we discussed were basic two-phase locking. So what is it? Just the general basic two-phase locking, what does that tell us to do? How does that tell us to approach our schedule? Or if you'd rather tell me strict two-phase locking, since that's what we use a lot in class, I'd be happy to accept an answer for that as well. I know you know it. Let's get some other people in on it. Yeah.
Strict two-phase locking, you acquire all locks in one phase and then release them all at the same time.
So actually, I would say that's probably basic two-phase locking, although strict two-phase locking, does follow those rules as well, but there's a little bit of an additional wrinkle involved. Two-phase locking, the first phase is acquiring all the locks, and then the second phase is releasing all the locks. Strict phase adds another additional restriction onto that process. Did you?
Yeah. So basically,
Security two-phase locking is that before you release that lock, you should obtain all the locks.
Right, so I'm going to obtain every single lock that I need. Hang on a second. Strict two-phase locking is, I mean, two-phase locking. So even basic two-phase locking says that I'm not going to release any locks until I've acquired all of the locks that I need for a transaction. What strict two-phase locking says is a little bit more nuanced than that.
I have a question. Isn't acquiring all locks conservative two-phase locking?
Well, it depends on when they're being acquired. So that was another type of locking that we discussed. Conservative two-phase locking actually will acquire the locks before a transaction begins, whereas strict two-phase locking will acquire them as part of the transaction itself. That's the main difference between those two locking schemes. But the way that strict two-phase locking acquires and specifically releases the locks is where it gets its name, strict two-phase locking. It's going to do what exactly? We still haven't quite nailed it down. It's going to hang on to all of the write locks until the very end. It might release some of the read locks early if it needs to, but strict two-phase locking will not release any of the write locks until the entire transaction has finished, even if it no longer needs those locks. It's going to keep them all the way until the end of the transaction. That's the definition of strict two-phase locking. Conservative two-phase locking is the same with the distinction of acquiring the locks before the transaction's even begun. And basic two-phase locking, which is never really used, says you can release a lock as soon as you're done with it at any point of the transaction. There are other flavors of two-phase locking, but those are the ones that I believe we talked about the most in class. And strict two-phase locking in particular is the common implementation that's used across many different databases. So we also spent some time talking about deadlock detection and deadlock avoidance. I don't want to go through every single option here, but who can give me at least one way that we handle deadlock in our schedules, in our transaction? Go ahead.
Some sort of a ticker.
Some sort of a ticker? Like a timer, you mean? Or I mean, so we talked about deadlock detection schemes being things like I guess it'd be more, yeah, deadlock detection being if a transaction waits too long to acquire a lock, we're going to assume that it's not going to get the lock and then abort that transaction. So that's maybe one of the simplest forms. They do come in more complex varieties though, such as constructing graphs that dictate, which transactions are waiting on locks from other transactions, seeing if any cycles appear, for example. And then the last topic about locks that we talked about had to do with the granularity of our locks. So we discussed that it's actually useful to be able to lock things on various levels. I might not want to lock everything on the row level. Sometimes I might want to have locks on the table level or even the entire database level, perhaps, if I'm making large-scale changes to things. And we talked about how that changes locks. There's actually a specific type of lock that gets introduced if I'm dealing with these more granular types of locks. What kind of lock is going to be used in that scenario? We have to extend it out. We can't just use plain read-write locks anymore. What else is going to be thrown in the mix? It's been a long semester, huh, guys? Are we just not feeling it today, or what? Yeah. That's the intention locks, yeah. That's the intention locks. So we'll use that tree structure to track track the various levels of granularity in our database, and then use intention locks to declare that we intend to acquire actual locks on items further down the tree. Yes.
So just to clarify, so an intention lock is like an intention lock itself. Would ever that be used to lock something, or is that just to notify anybody who is trying to get the actual read or write locks further down? This is what the situation.
It's more the latter. If I have an intention lock, that's actually not enough for me to perform an operation on an item. I have to have the actual read or write lock to make that happen. But it is a way of signaling to other transactions that I intend to acquire that lock, that I am in the process of acquiring that lock. So that they don't have to waste their time checking to see if the item further down the tree is available or not. Yep. We went through some examples of that in class. All right. So then we spent a big chunk of time talking about data distribution. We talked about a couple of properties of databases, some advantages of distributing our data. What are those two properties that I'm referring to here? The two main advantages of distributing data. Spent a lot of time talking about these. Yeah.
Availability.
Availability, and what's the other one? It's a similar term. Yeah.
Reliability.
Reliability. So what's the difference between the two? This is something that we spent some time talking about. It's a confusing concept. It's not very intuitive. Availability is the one I feel like we spent talking about the most. How do I measure availability? What's an example, a metric that I would use for availability? Yeah.
The percentage of how much time the server is up.
Uptime, yeah. Uptime as a percentage, sure. So this database was available 99% of the time. That's an example of availability. Whereas an example of reliability, a metric would be something like mean time between failures. How long on average does it take before some part of this is going to fail, or the entire system is going to fail, for example. We talked about different ways that we can partition data. There's two actually different ways that we discussed partitioning data. Who can give me one of those two? Go ahead.
Horizontal.
Horizontal partitioning. So horizontal partitioning tells us to chunk it up by the rows. I'm going to take some rows and send them over here. I'm going to take other rows of the same table and send them over here. And the other form would be vertical partitioning, which tells us to chunk our data up by columns. So I'll send some columns over here for a table and other columns over here for a table. If I use vertical partitioning, how do I join those partitions back together when I need to? Yeah, I got to send the primary key with each piece, and then basically perform, it's not exactly a join, right? But it's kind of similar in some ways to performing a join. Whereas horizontal partitioning is very much like a union, taking two sets of data and unioning them together. Cool. Then we spent some time talking about data transfer costs and how the system is responsible now for trying to determine the most efficient way of processing the queries. So I now have lots of different nodes, and I'm going to have to acquire data potentially from multiple different places to perform a given task. And so we then have to decide, okay, which of those positions should I grab the data from, for starters, and then where does it make sense to do the actual work? Should I do it on one of those other machines? Should I just get all the data back here and do all the work here? And the answer may change depending on lots of factors, like what is the operation that I'm performing? What's the size of the data that I'm going to have to be sending, etc. So we went through a couple examples of that in class where we did the math, did the arithmetic, and computed some costs for some actual problems. And then We also spent some time talking about the three-phase commit protocol. This actually is a very similar concept to what we just talked about with the data transfer costs, right? Transactions are now going to be spread out across multiple systems, which means that those are going to require an added layer of communication to function properly. We talked about how the three-phase commit adds an extra phase to the commit portion of the distributed transaction, so that if if the node in charge of the communication fails for some particular reason, the remaining nodes can still try to pick up and finish the transaction. Basically, it adds one extra little communication step. Instead of just telling everybody to make the commit, we get confirmations from all parties involved that they are in fact ready to commit before beginning the actual commit process. Yeah, what's up?
Just confirm on the three-phase commit, because I'm in the notes I focused on on the split of the commit phase, but the page that occurs before that is make your change, prepare to commit, and then commit.
Yes, those are the three phases. Do whatever you want to do, prepare to commit, and then actually commit. The problem with, the reason we need that middle phase, the prepare to commit phase, again, has to do with if everybody's waiting to receive a message saying that you should commit, but that node goes down, then everybody will sit there waiting, and nobody will receive that message. However, if we have messages about preparing to commit and that node goes down, then we can actually ask around and say, hey, did you guys actually say you were ready? And they'll be able to answer that question. Yeah.
Can we go over three phases?
Can I go over it again?
Yeah.
Okay, so the phase that we are introducing is a phase called prepare to commit. So instead of just having a single message coming from the transaction manager saying everybody commit your work, we're now going to have acknowledgments from each of the nodes involved saying that they are ready to commit, so that if the global transaction manager goes down, whoever steps into its place can still communicate with those transactions and see that they were all ready to commit and still perform the final commit operation. Whereas before, that information would not be available. Any other questions so far? So security is actually what we just talked about earlier this week. We talked about user-based control. So that deals with individual privileges. What privileges do you have on a particular relation or on the database as a whole? And then we talked about how managing individual users got to be a bit too cumbersome. So role-based control is now sort of the modern standard. We're going to group our users together into various categories and apply privileges or revoke privileges, as the case may be, to those individual roles. And then we talked about this actually before. We talked about this actually earlier on in the semester as well, but we also went through another example of SQL injection on Tuesday as well. I think these are the last two topics. Yeah, these are the last two topics. All right, data warehousing. So data warehousing is something that we just talked about last week, not too long ago. And the main design for a data warehouse is not an ER diagram, but what kind of modeling are we using for data warehouse? Anybody?
Fact tables and dimension tables.
Fact tables and dimension tables. It's actually multi-dimensional modeling. Those are all parts of multi-dimensional modeling. So who can tell me what a fact table is then? What role does the fact table play in our multi-dimensional model? this is your guys' time. I have put this time aside for you all to help you review for this exam. If you don't want to contribute, then it is your time that is going to waste. Yeah.
Fact tables, something really say, but they typically contain facts which are like the true data.
The true data, yeah, you're very, very close. You're super warm. We're looking for things that are quantitative, things that you might hear them referred to as measures, right? Things that we can actually quantitatively measure about a particular event. So each row in our fact table is going to represent one event that has taken place and any quantitative data that we have decided to measure and record about that particular event. So the classic example of that would be a sale that has taken place. We can record things like how much money was involved in the transaction, for example, as one type of measurement that might be taken. And then the other part of our multi-dimensional model, besides the fact table, were the dimension tables. So what do the dimension tables do for us in this model? Yeah, go ahead.
They're more of the descriptors, the things that you're going to want to aggregate by. So
Yeah.
region, product type.
They provide the context. So anything that is not necessarily quantitative, but more of a description about what's happening. So where did this happen? Who was in charge of this event? When? So time is going to almost always be a dimension in any data warehouse. I'd be very, very surprised if time wasn't involved somehow. So, you know, those kinds of questions that provide context are going to be our dimension tables. So the facts table then has a link to all those dimension tables, right? The main components of a facts table are the measurements that we talked about, and then foreign keys pointing to each of the dimensions that are involved, indicating the context for that particular dimension. The dimension tables themselves are going to just have tons and tons and tons and tons of descriptive information. And so that actually forms the basis of our data warehouse. And in order to interact with our data warehouse, we are going to perform some operations called cube operations, because you can envision the different dimensions on the edges of a cube, for example, although it doesn't have to be a three-dimensional cube. It can be as many or as few dimensions as you would like to include. What are some of the operations that we talked about last week that can be performed on these cubes? Yeah, go ahead. So we can remove a dimension. What kind of operation is that? I'd call that a slice. Yeah. What are some other operations? Yeah. Roll up, which means aggregate. We're going to take the values in the cube and we're going to aggregate them together. So this could mean summing, this could mean averaging, this could mean taking the max or the min, but we're going to aggregate. And typically those aggregations are going to occur at particular points of our dimensions that we call levels within a hierarchy. So dimensions oftentimes are going to contain hierarchies. A classic example of a hierarchy is location. We are currently in a building that is on a campus in a city, in a state, in a country, on a planet, in the universe. So those levels would be various natural places that we might want to do some aggregations. We can do the opposite of rolling up as well, which is drilling down. However, the limit with which we can drill down is defined by what? We can only drill down as far as what allows us. Yeah. The granularity of our fact table, right? The granularity of our fact table is basically saying, all right, what does one row in our facts table represent? So if we're talking about sales, it could represent one sale that has taken place at a given time at a given store, right, with a given customer. That would be how I would define granularity, as a function of the dimensions involved in the fact table. And so we spent some time too comparing this new way of thinking against the old way that we've been, well, it's not really old, it's just a different way of setting up databases, the way that we've used for most of the semester with ER diagrams and going through third normal form to normalize our databases. And so there are advantages of the online transaction database, which is the ER diagram format, the normalized format, and the online analytical database, which is the data warehouse. Which what operations are the online transactional databases optimized for? What kinds of database operations are going to perform better on a database that has been put together using ER diagram, third normal form, that whole bit? You got two options. Yeah. Updates, writing data is going to be optimized for that particular database. You think about why that is the case. The whole point of normalization is to remove redundancies as much as possible. That's going to make updates a lot faster, because if I want to change something, I know that there aren't any redundant pieces out there. It's just in that one spot. Makes it very easy for me to locate and make the modification. Whereas in a data warehouse, we're actually not normalizing our data. We're denormalizing it, meaning that I'm going to see the same data appear in many different spots potentially. So if I want to change that data, it's not going to be a necessarily easy task. I'm going to have to find every spot that it appears and make that change. However, the advantage of that is that our analytical databases are then optimized for the other kinds of operations, the retrieval, the database reads. And there are many reasons for this. Actually, the reason that I just described is one of them. The redundant data makes it easier, because typically to access that data in a transactional database, what would I have to do? I'd have to do a lot more joins. I'd have to join a lot more than I do in an analytical database. And joins are expensive. Joins take time. We've talked about that in previous classes. By denormalizing our tables, we have fewer tables, and we have less complex structures in our analytical databases, which means fewer joins, faster retrieval times, but again, at the cost of updates. Updates are going to be very poor. All right, last but certainly not least, we spent a big chunk of time talking about NoSQL databases. So there's a lot of types of NoSQL databases. We only covered 3 different types in class. There are more that I did not have time to get to. The main one, of course, that we talked about was Mongo, and that's what you've been spending some time working on with this most recent homework assignment as well. And so the things that I might expect you to know on that, of course, anything that's on the lab is fair game for the exam. So basic usage of Mongo, how to construct documents and work with those documents at a very basic level is all stuff that you might see on the exam. And for that database in particular, since we had a whole assignment on it, I think that there's lots of potential for some coding problems in there. I think it's pretty safe to say that for the other types of NoSQL databases that we talked about, probably not going to ask you to do some coding kinds of questions, but I may still ask you some conceptual questions about things like the graph database that we saw, for example. What is the graph database trying to exploit? What is the main advantage of structuring our data using that graph style database as opposed to the tables with rows and columns that we've been used to? What's the advantage there? So the tables are gone. There's no rows, there's no columns. But I do see something that looks kind of familiar from a relational database. In fact, I see a lot more of it in a graph database than I would in a relational database, typically. Go ahead, John.
It maximizes relationships.
The relationships. There are lots of relationships. So in a relational database, we also have relationships. They do exist. That's actually a time-consuming part of the process, but they're useful. Otherwise, we wouldn't, go out of our way to include them in our designs. But they are slow. They are a performance issue. Graph database tries to meet this issue head-on and say, well, let's make a database that performs well with relationships. We'll just use relationships all over the place, and those are represented as edges between the nodes. So if you have a data set that is very relationship heavy, a graph database might suit your needs better than a traditional relational database would, perhaps. We also talked about Redis, which is a key value store database, as the last kind of database that we discussed. I think the most interesting about Redis is it's entirely in-memory database, right? So that severely limits what it's capable of doing. It's not a very big database, but it is very fast because everything is in memory. That's what it's going for. Okay, I think that's all the topics that we've talked about since the last midterm. So as you can see, I've got some exercises here on this slide deck. I've also got a couple of past exams that we can talk about. Or if you just have general questions, I'm happy to answer those as well. But this is the time where I'll turn things over to you all and see what kinds of things you would like to work on or discuss for the remaining time in class today. Yeah, what's up?
I think you said it before, but final is or isn't?
Is not. It'll be on these topics. What else we got? Yeah.
If no one else minds, I wouldn't mind if we just start working through the examples.
Okay. I mean, sure. Unless anybody feels strongly, then we'll just start with the first one and see how far we get. So here's an example with a few slides, and you can see your task is to answer a few questions about these schedules, including what conflicts exist and questions about their serializability or not. That last one about deadlock is actually a little tricky. You're going to need to think about that one a little bit. But I'll give you a few minutes, talk to your neighbors. I'll be around if you have any questions, and then we'll go through this together in just a little bit. Okay, we can actually answer the first two questions by doing, the same thing, which is constructing the graph, the precedence graph. So let's go ahead and do that. In order to construct the precedence graph, I need to draw my nodes first. So what do I use to draw the nodes? How many nodes am I going to have? Two. One for each transaction. And then the next step is to start drawing edges between these two nodes. How am I going to decide whether or not to draw an edge? Can somebody give me an example of an edge that should be drawn between these two nodes? Go ahead.
If a right occurs after, and if a right occurs after a read to the same thing.
So a read-write conflict
Right,
or a write-write conflict, we're looking for those particular conflicts in the schedule. So I assume we have at least one in here somewhere. Could somebody point out a conflict that we got? Write read from where to where? Okay, there we go. W1y to R2y down here at the very end. And so then the algorithm tells us to draw the edge from where to where? Am I drawing it from 2 to 1 or from 1 to 2? That's our options, right? 1 to 2? From the earlier operation to the later one? The secret is it doesn't really matter as long as you're consistent, right? As long as you consistently draw it from the earlier to the later or from the later to the earlier, it doesn't matter. So draw it from 1 to 2, so we're drawing from the earlier ones to the later ones. Are there any other conflicts? Any other conflicts? Right read from where to where? Z, yeah, Z here. But that's the same edge, right? So I don't need to draw it again. But yeah, it is a conflict. That is true. I think that's the only conflicts that can possibly exist, because a conflict has to have a right involved. So this is the only conflict edge. This is the only edge in our graph, which means that this is serializable. This is in fact serializable. Let's take a look at the other one real quick. Okay, so now I've got 3 nodes. And where are the conflicts? Who can point one out for me? Yeah.
1 to 2.
1 to 2
Like
based on
R1Z and then W2Z.
So this guy and this guy, right?
Yeah.
All right. What other ones do we have? 2 to 3, which is right here, right? 2 to 1 based on what?
Y.
Based on y, so from here to here. Any others? X is only used once, so that guy's not going to be a problem for us, right? I don't see X anywhere else. Here's a Y. That's another 2 to 1 right here on these two rights. Here's from 2 to 3 based on Z, right? We already have that edge. 1 to 3 based on this. R1, oh, the first one and the last one, right? 1 to 3. Unfortunately, I mean, we could have stopped a while ago because this is not conflict serializable. We've proven that. Because there is a cycle between transactions 1 and 2. There's a cycle. So this one is not conflict serializable. It's almost conflict serializable, but not quite. Okay. So for that first one, if I can go back to that one for just a second. For this first one, right, we declared that this one is conflict serializable, meaning that it is equivalent to a serial schedule. In order to prove that, what would I have to do? In order to actually strongly prove that that was in fact conflict serializable, what would I have to do? Yeah.
Rearrange it so that all of the operations for transaction 1, or one of the transactions finished before the other one finished.
So you're close. I mean, I think to really prove it.
And then so you have to say that.
We have to find the serial transaction, or find the serial schedule rather, sorry, that would produce this exact same graph. So there's only 2 serial schedules in this example because there's only 2 transactions. I either run transaction 1 first or I run transaction 2 first. Those are my options. But one of those 2 serial schedules, or I guess possibly both, would generate this exact graph, meaning that they are conflict equivalent. And then the last question on this slide is actually a bit more involved. So will there be deadlock? We actually don't have enough information right now. Where did that come from? Go away. To make that assessment. What additional information would I need to make that assessment? Yeah. I gotta know where the locks are, right? So that's something that we could do, assuming that we want to follow strict 2-phase locking, which if this were an actual exam question, it would be a lot more explicit. I wouldn't leave it as open-ended as this, but this is still something that we could do, right? I need to insert statements to show where the locks were going to be acquired, and then I would also need to insert statements in these schedules to show where the locks would be released. And once I have that information, I would then be able to determine whether or not deadlock was going to exist. For this first one, it's actually relatively simple. Transaction 1 would need locks for X and Y at the beginning, right? And transaction 1 would need to acquire locks here. If I can write this down. Transaction 2 would need to acquire locks here. So they would both need locks for X and Y, but only transaction 1 needs a lock for Z. Or no, they both need for Z as well. Sorry, I missed that. So they would both need to acquire the locks that they need. T1 needs, what kind of locks? Let's see, for X it just needs a read lock. For Y it needs a write lock. And for Z it needs a write lock as well. Transaction 2 needs a read lock for X, a read lock for Z, and a read lock for Y. Is it not doing any? I guess it doesn't do any of the writes. Yeah. Doesn't do any of the writes. So just read locks for all of those. So X is not going to be our problem. X cannot cause deadlock in this situation, right? Why not? There's no write locks involved, so X is not going to be the problem, but Y and Z potentially will be. And what's the verdict? Do we think the deadlock's maybe going to happen, or are we clear? Yeah.
I can't think they wouldn't happen because only transaction 1 ever wants to write to me.
Only transaction 1 ever wants to write, but consider that transaction 1 is going to acquire the write lock for Y and the write lock for Z first thing. So these locks will be acquired here, and then transaction 2 wants to acquire the read locks for Y and Z shortly after that, correct?
Yeah. But
But it cannot do so because these write locks are still outstanding.
Okay, so is the criterion for deadlock just simply if a transaction would not be able to require a lock on demand?
More or less, yeah.
Okay.
If I can't acquire that lock, yeah. For a given schedule, right? I might be able to take these operations and rewrite them in such a way in which the schedule would, avoid that particular situation. But yeah, question?
I have a question about the relationship between deadlock and conflict.
Okay.
Since we proved that there's no conflicts in this diagram, right? So we need to still.
Well, there is one conflict at least, actually two. Yeah, two conflicts.
No, I think the first conflict just proved there's no conflicts.
No, there's a conflict between transaction 1 and transaction 2. Yeah.
So basically, if we prove there's no conflict in two or more transactions, which means there's no deadlock.
So if there are truly no conflicts, then yes, deadlock's not possible, because no conflicts means that what we need to be careful though, right? We need to be very careful. If there's no conflicts, I don't believe deadlock is a possibility, because they're either not accessing data items, the same data items in such a way that would cause it, or it's just all reads, right? In which case deadlock's not going to happen. But we need to be careful. Just because I have proven this as conflict serializable does not mean that I can make any assumptions whatsoever about deadlock. That's a totally separate thing. Something, in fact, I mean, this is an example of something that is conflict serializable that would potentially lead us to deadlock. Okay. Right? They're two totally separate things. Yeah.
Just try to extend another concept. If you can prove that you have a conflict on your schedule, does that mean deadlock is always a possibility?
I think always a possibility is probably a fair thing to say, yeah, but it's hard to guarantee it one way or the other. I can't say that it will or will not happen based only on the conflict serializability graph. It's not enough information. I need the locking information. Yeah.
So if there were any more transaction 1 happening after the write policy, would there still be a deadlock?
Say that for me one more time.
So I mean, I feel like based on if we're doing this in a strict two-phase lock, you said write lock is always obtained until it is either committed or avoided.
Right.
So that's
correct.
why we're assuming there could be a deadlock too, but we want to see it on.
The conflict has nothing to do with the locking.
But I think we just mentioned there could be a deadlock because there's a write lock on this.
Correct.
When there could be shortly after.
But deadlock would happen up here when the locks are acquired. Transaction 1 wants to acquire a write lock on Z. Shortly after that, transaction 2 wants to acquire a read lock on Z, because two-phase locking says I'm going to acquire all of my locks before I do anything. So these two arrows in the schedule indicate where those locks are going to be acquired. Transaction 2 cannot acquire the read lock for Y or Z at that point in time, because transaction 1 still has the write locks for Y and Z. It cannot possibly acquire those at that time. And so then the question becomes, all right, eventually transaction 1 will release those locks, correct? But it will not do so until it's completely finished, which happens over here. So at this point, transaction 1 is finished. It will then release those 2 locks, meaning that at that point in time, if transaction 2 wanted to acquire the read locks for those particular items, it could do so. I think what's interesting to note, though, is that like I can have a different schedule than this. I could rewrite this schedule, just reorder the operations. I could rewrite it, and it would still potentially have this same conflict graph, but not have deadlock. That is entirely possible. In fact, that's what we want to happen in our cases, right? Is we want to create a schedule that is conflict serializable and does not have deadlock. In practice, what would actually happen, right? We would actually try to run this schedule. In practice, we would try to run this. It says it's conflict serializable, so all right, cool. That means we can do it. We can run it. We would either detect or see ahead of time that deadlock was going to happen, and then try to do something to fix it. Abort a transaction, tell it to come back later. Which, when I abort a transaction and tell it to try again later, what am I effectively doing? I'm rewriting the schedule, right? I'm removing all of that transaction's operations from the schedule and pushing them later. Pushing them down the road, and hoping that at that point in time, it'll be able to acquire the locks that it needs. Right? So just because the schedule is conflict serializable does not actually mean that that is the schedule that's going to be executed or that it can be properly executed. If deadlock occurs, I got more work to do. I have to do something about it. Yeah.
Just one more question. When we put that T1, that T2 there, does that imply that we're using two-phase conservative locking? Because, like, I think my current notes is that conservative is where you acquire all locks before you begin the transaction. That's kind of what looks like it's going on in the way that we have it written here.
Well, I think it could be interpreted either way, right? I mean, I don't have any markers here saying transaction start or transaction end. If I truly wanted to know where those locks are being acquired, I would need some indication of that. But right now, there's not enough information to make the distinction either way, in my opinion.
Okay, I just feel I'm going to get tripped up because it seems like basic two-phase locking is just all locks should be acquired before the first unlock statement, and that,
so basic
that means it's like, yeah, I can just grab the X lock right now. Then later on when I need the Y, then I'll grab that lock. And I'll go ahead and do my reads, and later on I'll grab the Y lock and do that.
So basic two-phase locking would say that T1 could let go of the right lock for Y here at that point. That's what basic two-phase locking says. Strict two-phase locking says that's not possible. You can't release it until you're entirely finished. That's the biggest difference between those two. The biggest difference between conservative and strict two-phase locking is consider that if I am acquiring locks as part of the transaction, I could run into deadlock. We've seen that, right? If I am acquiring locks outside of the transaction, I'm likely going to avoid the issue of deadlock entirely because I'm not even going to start the transaction, right? I'm not even going to start it if I don't get the locks that I need. So you could consider strict two-phase locking as a more optimistic form of two-phase locking. It's like, well, I'm going to assume that I will be able to acquire these locks. I'm going to try to do so and wait until somebody tells me that I can't. Or a strict two-phase locking might also be banking on the fact that if deadlock does occur, that it's not going to be the aborted transaction. Maybe the other guy will be the aborted transaction, and I'll be able to keep going, right? Whereas conservative two-phase locking is saying, well, I don't want to run the risk of being the transaction that gets aborted and has to be restarted later. I'm not even going to try to do anything if I can't get my locks. Yeah.
Well, so does that imply, going back, that when you did that, like for example, that write one Y, that you committed it as well?
The commit doesn't happen until the very end.
Well, because according to my notes, it says you don't release any write locks until you commit or abort if you're doing strict.
So that would happen after all of the operations are finished, which is at the very end. For transaction 1, right, this is the last operation, right. So I can commit right here.
Right.
Transaction 2 needs to wait until it's done one step later.
Okay, so the earlier arrow was for basic two-phase?
This one?
Yeah.
Releasing a lock for basic two-phase, yes.
Okay.
Any other questions? We got time to probably do at least one more. That one's a bit too open-ended. Let's see. Maybe we can do one of these data warehousing ones since we didn't actually get a chance to do a lot of those in class the other day. Let's take a peek at this exercise. So we're starting with a data warehouse. We're starting. I give you the dimensions here, right? And the measurements involved. So I want to see the schema. When I say include attributes for each dimension, you don't have to go crazy with it, right? Just put down a couple examples. You don't need a ton. You don't need a huge list. What I'm more interested in this problem are the last two bits, which is the cube operations in particular. I think that middle question is probably the most important one. So I want to know what cube operations would need to be performed. And then this last one is kind of interesting, but I'm not as concerned about it as the cube operations. Writing a SQL query to actually perform the cube operations necessary. I'll give you a few minutes to talk about this one with your neighbors, and then we'll sketch the solution up here in just a little bit. The issue is that weighting of changes are also transaction 2 is the weighting of transaction 1. It can't happen so much. Rewrites the entire. If I need to execute these operations in this order, it's not going to happen because we don't still need weight or one of them is going to weigh and not be able to acquire.
I'm showing count. Count number charge. So I guess the data table diagrams or like a business. Doctor name, location, day. Here's doesn't. But that's the schedule. So we have to do the process all over.
Start schema. Yes, it is. I can start at one node and take edges and end at that same node every cycle. It doesn't matter how many edges I have. That's it doesn't have deadlock because this transaction starts with no proper line. All right, we're running out of time here, so let's see how far we can get with this with the few minutes that we have left. We first thing we want to do is sketch up our data warehouse, what it looks like. And so the way we do that is with a particular kind of schema called a star schema. So I'd see a fact table here in the middle. And then the columns that I would expect to find in that fact table would be what?
Date key.
So I would need foreign keys for the date, the doctor, and the patient. I'm not going to have enough room to do this. What other columns? Yeah. Count and charge, the measurements. Sorry for the sloppy fact table, but that's what it would look like. I'd have foreign keys and then the measurements. All right, and then I would need additional tables for my dimensions. So I'd have a date dimension over here. That would be tied to that key. I would have a doctor dimension. And a patient dimension. And so I'm not going to write down attributes for these. You can kind of probably reason about what the attributes might look like for such a set of tables. We'd have names and addresses and things like that for the people who are involved, and dates have months and years and stuff involved. But this is our star schema. This is our basic star schema that would exist. So the next question is the one that I wanted to actually spend some time talking about. So we're going to start with a cube that has dimensions of day, doctor, and patient. Those are the base levels, right? The base levels. And so we want to know what operations we need to find the total fees collected by each doctor in 2009. And so what I like to do when I approach these problems is start off with the base cube. So I get to test my cube drawing skills today. Not bad, I guess. Looks a little weird, but that's okay. And then I've got day on one axis. I've got doctor on another axis. And then I've got patient on this axis. Okay? And so I would have cells in here. We don't have any actual data to put in these cells, right? But you can imagine that across this vector, I would have one, row for each doctor in my database. Across the day, I would have one row for each date, right? Across the patient, I'd have one row for each patient. So the question then is, all right, starting from here, what cube operations do I need to answer this question? Anybody have any ideas about that? Yeah, go ahead.
For day, you would need to slice out all non-2008s and then roll up all the ones that are left.
Right. So we need to. So I'm at the date level, right? So I need to aggregate those up to the year level. That's a hierarchy, right? So I need to aggregate those up to the year level and then extract out all the years that are not 2009. Just get those out of there. So that's a roll-up operation and a slice or a dice operation to take care of that dimension. What else would I need? I think there's actually only one more. Yeah.
Just a question. So you're saying you're going to roll up by year?
I'm going to roll the days up into the years. Yes. Yes.
Then you'd also need to roll.
That kind of happens as a natural side effect, right? If this axis switches to years, then the data inside of the cells now deals with years. I don't have to touch the other axes to make that happen. It's just a natural side effect of the aggregation process. I still have each individual patient on this axis.
Yeah, so let's say you would have to aggregate all those per doctor.
You would have to perform the aggregations necessary to make that happen, yeah. But on the other axes, they remain unchanged. So for now, although we do have at least one more change we need to make. One of these dimensions is necessary. Patient is not necessary. It is not a necessary part of this question. I don't care what patients were involved. I just want to see the total fees excuse me, collected by each doctor for a given year. Right? So what I actually want is not a cube, but a rectangle, right? And even more than that, right? I really just want something that looks like this, where each row is a doctor and then 2009 is the only thing that I see on the date axis, right? So here's what my cube should look like once it's finished. It's not a cube anymore, but still, I've got the date on the bottom axis with just 2009, and then I've got one row for each doctor in my doctor's table. The patients are removed. That's another slice operation to get that dimension out of there, to just remove all that patient data. And then we aggregate up by aggregate our dates up to years and then slice off the years that we don't care about. Cool. I think that's all the time we got. If you have any other questions, I can stick around for another minute or two. Of course, ask me on Piazza if you have questions about stuff, and I'm going to post some office hours for next week as well sometime soon, so keep an eye out for that. Thanks, everybody.
Just one quick question, because I'm going to try and finish this one at home.
Sure.
If we're translating